Hi there, guys. Hope you're having a nice weekend so far. In this video, I want to show you guys how to integrate this particular function. We have tangent of 2x. And you might be wondering why I decided to make an entire video just for one particular function. Well, if you watch the most recent video I uploaded before this one, you will remember that we covered a way of doing u-substitution problems in our heads without writing down all of the steps. And it helps us to get our answer much quicker and much more efficiently. And this was part of that last video, but I decided that this problem is maybe a bit too advanced for the topic I covered in the last video, and that's why I decided to make a completely separate video that would kind of give us a good idea of how to integrate something like this. So at first, it doesn't even really seem that complicated. For example, what if we had something like this? It looks really similar to the integral of cosine of 2x. And we know exactly how to integrate something like this. So if we go by the tools we used in the last video, and I encourage you to go watch the video that I uploaded immediately before this one to understand how to do this kind of a problem mentally. So when I'm doing this mentally, I'm doing the u-substitution in my head without writing any steps down. I get 1/2 sine of 2x plus c. Again, I did this completely in my head, didn't write down any steps. And I get the same answer as I would if I did the u equals blah, 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 and the du equals blah, blah, blah. But we don't actually have to write anything down at all. So we have this, and then you might be thinking, why can't we do something similar with tangent? Well, it's because tangent doesn't have a clear elementary antiderivative. I mean, I guess in technical terms it probably does, but it doesn't have a clear way to integrate. That we probably don't have the antiderivative of tangent committed to memory as we do the other trig functions. So actually, we can't. I don't really think we can do this mentally, but I still felt like it would be a good idea for me to show you how to integrate this. It is fairly complicated, and it may even seem impossible at first, but it is possible. We're going to have to use kind of an advanced method that I don't think I've ever covered in any of my classes before. So I feel like this is going to be multiple iterations of substitution, of u-substitution, and I'll show you what that means real quick. So because most of us probably don't have the antiderivative of tangent committed to memory. What we do know is that tangent can be written using one of those trig identities. We can use one of the quotient, sorry, not the quotient. Yeah, I was right the first time. I'm losing my mind, you guys, if you haven't been able to tell already. We can rewrite tangent of 2x using that quotient identity from pre-calc. We can write that as sine of 2x divided by cosine of 2x. Integral sine always goes on top for tangent, so we have sine of 2x upstairs, and then downstairs we have a cosine of 2x dx. And it's much better to have this than it is to have whatever appears on top, because we do know the derivatives and antiderivatives of cosine and sine. We know those pretty well by this point. And if we didn't have 2x, we'd be on easy street right now. It'd be really, really easy to integrate this if it were just a sine of 2x divided by a cosine of 2x. But the problem is, sorry, I meant to say it would be easier if we have sine of x divided by cosine of x. But this one is not like that. It's a bit more advanced, it's a bit more complicated. Just because we have a 2x on the inside instead of just a plain old x, things are much more complicated than they would otherwise be. So we have to think of a way to make this work. So what we want to do is we want to do one substitution. We're going to start with the u-substitution. We're going to have u, of course, be the inner function. So u is going to have to be 2x. And notice how what function we have upstairs and what function we have downstairs both include that very same inner function. So we did u equals 2x. We took the derivative of both sides. We get the derivative of u with respect to x equals 2. And then we're going to have to do that separation of variables we see all the time. Multiply both sides by dx, and we get 2 times dx for the derivative of u. The problem is we have this 2x in the integral, but what we don't have is the 2. So we're going to have to take this a step further, and we're going to have to divide both sides of our differential equation by 2. When we do that, we get 1/2 du equals dx. And this works out really nice because we can take this dx, we can replace dx with 1/2 times du. Makes things really easy. So what I want to do is I want to rewrite the integral. I'm going to write this as sine of u because we know u is 2x. I'm going to write this as a sine of u divided by a cosine of u. Whoa, what happened there? My computer acts up sometimes. Sometimes I have to threaten to throw it out the window and then it starts working again. Not sure why that is. I don't know why it works, but it does. It does work. So I'm going to replace dx with 1/2 du. So this right here times this is equal to dx. So I just replace dx with the product of these two things, and I move the 1/2 outside. And it doesn't even really seem like it helps that much to write it like this. But we're about to see just why this is so useful. I want to do a little bit of spring cleaning, move this stuff up here to be dealt with later. And then I'm going to do another substitution. I'm going to do what I call a v substitution, or maybe a w substitution. I try not to use u and v in the same problem because then it tends to get confused with integration by parts. So remember that integration by parts problems involve a lot of u's and a lot of v's, and a lot of du's and a lot of dv's. So that's why in a problem like this, I try to avoid using v after u. So I'm going to use a w instead. So we want to decide what function would be w and what function would be a dw. So we can see that we're going to have w be whatever appears downstairs in this rational function. It just doesn't work to have the function itself on top and then the derivative on the bottom. We would have something like this, and we can't do that. We can only do problems where the derivative of the function happens to be on top. We can't have 1 over dw. So that being said, we're going to have the thing that appears on the bottom of this fraction, we're going to assign that to be w. We're going to have w is cosine of u. And then we're going to have dw, derivative of w with respect to u. The derivative of cosine is negative sine. So this is going to be negative sine of u. And then we want to do another separation of variables. I want to move the du to the other side by multiplying both sides by du. But not only that, I also want to multiply both sides by a -1. So that way the dw is negative instead of the sine. So we're going to have negative dw equals positive sine of u times du. And this works out really nicely because if we take this integral and draw a box around all of this stuff, we can see that now what we can do is we can replace everything on the inside of this box with a negative dw. We know from the differential equation that negative dw is equal to sine of u times du. So we can replace sine of u du with just negative dw. And then we can replace cosine of u with w. So we have, I'm going to take this negative sign, I'm going to move the negative out front, so it's going to be a negative 1/2. Negative 1/2. And then this turns into a positive dw over w. And this is a really common integral. We remember that this has to be natural log of w when we integrate this. Whoa, not sure what happened there. So if we take the antiderivative of dw over w, we're going to get natural log of w plus c. So we have negative 1/2 natural log of w plus c. So we have our final answer, but we're not quite finished yet. We have to plug things back in where they belong. So we have to plug in w into this complete solution we have just found. So we're going to replace w with cosine of u. And I'm going to write it up here because I'm running out of room down below. So I'm going to write this right here. We're going to have negative 1/2 natural log, not natural log of w, but we're going to replace natural log of w with natural log of cosine of u. Plus c, and then we're not quite finished yet. One more substitution we're going to have to do. So we want to take this u, and then we want to replace u with 2x, because remember when we started this problem, we assigned u to be 2x. That is the inner function of the original integral that we're given. So I'm going to replace u with 2x, and we're going to get this. We're going to get negative 1/2 excuse me, we're going to get negative 1/2 natural log of cosine of u. And u is just 2x. We're going to get negative 1/2 natural log cosine of 2x plus c. And there you have it. Hope you found this useful. Hope you guys enjoy the rest of your weekend, and I'll see you next time. Bye.